At the purpose of this video, go over AP Practice Problem 4. Once again, look at the answers, and then we'll look at the key as to how they assign the points and what you need to say to get full credit. All right, this problem revolves around people who work in New York City, and they're recording their physical activity, so they're wearing trackers. So their population are people, not just workers in New York City, but workers in New York City who wear such trackers. So we have to be aware of that. So of these people who wear trackers, they're walking around and they're getting their steps counted. They decide to pick a random sample of 61 of these people. To sort of get an idea, like they want to know, well, how many steps are taken by the typical worker? Let's look at a sample, because obviously, if there's thousands or millions of people wearing these things, it's too difficult to collect all that information. So they use 61 people to estimate. They take the sample, and the mean is 9,797 steps, and the standard deviation is 2,313. So of all those 61 people, this was their average, and this was the spread. All right. So with that information, this appears to have the structure of a one sample T procedure, and the way I tell that is, there's a mean, there's a standard deviation, and it's from a sample of a certain size. So this is the inference that we did after school closed in those videos that, the one sample T interval and one sample T test and all that stuff. All right. So in fact, part A just gets right into, this is a typical inference question. It says, construct and interpret a 99% confidence interval for the mean number of steps taken on a typical workday for all people in New York City who wear the trackers. So basically, we took a sample of 61 people. The sample of 61 people is supposed to be representative, but it's not going to be perfect. Remember, the real value, or this value is basically going to float around the real value. It's likely that's close to the real value, and less likely it's farther away. So we're going to use this value, go, well, if this is supposed to be close to the real value, let's make a range for the real value. So that's what the confidence interval gives us. Now, the important thing, because when I grade this is what people forget, and this kills the grade. When you do an inference procedure, meaning you do a confidence interval or you do a test, you have to check the conditions unless they say otherwise. They didn't check the conditions for you. So when I was grading this, I see people come up with a great confidence interval, but they don't check the conditions. You can't make a confidence interval unless the conditions are met. So I'm checking the conditions. Once again, this is my scribbly garbage. I would probably be a little more meticulous on the test. This was just for me, for my key, or something to talk about as I was showing it to you. But you do need to check the conditions. So that would be a major problem right off the bat. You do all this great work and get a confidence interval, and you wonder why you didn't get full credit. It's because you didn't check the conditions. So what are the conditions for the one sample T test? You get to check these because you're taking the exam at home, and if you're taking the exam at home, I gave you that, or you can go download it online and print it out, or I think Favre might have mailed you one. Basically, there's the packet of inference stuff that gives you all these conditions. So on the test, you'd have to remember to check them yourself if you were taking the traditional test, but you can have this list right next to you. You can have your notes, or you can have the little packet I gave you. So make sure that you have that information available to you so you check the right conditions. So you have to check. Now, I think actually they don't make you check all the conditions in the grading, but I'm going to check them all anyway because that's how I taught it, right? And it's what you should do. The random condition you should check. It says it in the problem that they were randomly picked, right? I think I can see it right here. Random sample 61. Boom, they said so. So we're trusting them. Is the independence condition met? It's reasonable that one worker is not affecting another worker's, especially since they were randomly picked. They're probably not affecting each other's number of steps, right? So we have independence. That's good. We want to make sure we don't pick too many people. The 10% condition says don't pick more than 10%, but we're dealing with 61 people. That's surely less than 10% of workers in New York City. I should put workers in New York City who wear these tracking devices. New York City's got millions of people in it, so it's likely that there's thousands of people wearing this thing at the least, and 61's less than 10% of them. We also need to check, because it's means inference, we need to check the nearly normal condition. We want a large enough sample size to guarantee that a normal curve will work. On the test, they allow it to be bigger than 30, but like I said, I go by what I learned in college, and the textbook goes by the same number. So I go by 40, but you could put 30. The AP accepts 30. So 61 is greater than 40. or greater than 30, whichever one you want to use. Either way, it's greater. And what that means is the nearly normal conditions met. That means it's okay to use a normal curve. It's close enough to what the real value would be. And now that those conditions are met, I'm going to state what I'm going to do. Do the conditions met, we can perform a one sample t interval for the mean and make the confidence interval that they seek, right? It's valid to make this confidence interval because these conditions are met. So I called all that step one. Step two, in fact, I think they called that step one. That's one of the things they graded. Here's the second thing they grade, the actual confidence interval calculation. Once again, you can have all these sitting in front of you, all these formulas. So what's the confidence interval? It is, for a mean, it's your sample mean plus or minus the critical value, the t-star, times the standard error. The critical value is a t-score it's a sample of 61, so it needs 60 degrees of freedom. All right, so if you're going to do this by hand, I mean, you could put all this in a calculator and have it pump this out. But if you do it by hand, you need to realize, well, it's 99% confidence that they want. You'd have to cut this in half, add it to 0.5, and do inverse t with 60 degrees of freedom to get this t-score, which is 0.2660. That's how I'm getting this value. This value was what they gave me, and then the sample standard deviation was 2,313. Since we're picking samples of 61, that's the standard error, right? This is for the sampling distribution, not for the original data. So basically, we have their mean and their standard deviation used to get the standard error for the sampling distribution for the confidence interval. Put all of it together, you get this. If you know how to use the calculator to do a one sample t interval, you basically have to sort of state what you're doing, but you can just jump to the calculator answer here. When we go over it, we'll see what they ask for. They basically want this confidence interval. So basically, even though our sample came out as 797, what could the true population value be with a 99% confidence? Well, the true value is between 9,009 roughly and 10,584. All right. You then need to state your conclusion. So, I mean, I basically just said that, but, just looking at this isn't good enough. So I threw that over here. Step 3 is stating what this means. What does it mean? We are 99% confident that people in New York City who wear these trackers have on average a number of steps between those two values. So this is the interpretation of what that confidence interval means. And, they did say construct and interpret. That's why you have to do that last part. We have to construct it, so we have to check the conditions, we have to actually make it, and then we have to tell what it means. So that's this last part. And you have to be very careful about including everything. You can't just say, I'm 99% confident this is the number of steps, something that simple. You have to state it's the average number of steps in that range for that specific group of people. And that specific group of people are New York City workers who wear trackers, right? That's the specific population. So you have to be very clear about what you're stating. Think about that you're writing it for someone in a professional setting and you don't want to lie, right? You're published in a newspaper or something and you want to make sure that you're very precise about what you say, all right? That's the bulk of the problem. So because there's 4 parts to this problem. This is the fourth part, the very last question. So part B says, a wellness director at a company in New York City wants to investigate whether it's unusual for one person working in the city who wears an activity tracker to record approximately 8,500 steps in a typical workday. So they're thinking about an individual. Is it strange for a single person? I pick a person, would it be unusual for them to record 8,500 steps? So basically, that's the question. They want to go, is it appropriate to use my confidence interval? And the answer is no. The reason the answer is no is because the confidence interval is an estimate of the population mean. It's everybody's steps on average. It doesn't tell you about an individual. All right, so basically you can read my answer if you want. It says no, since the confidence interval gives information about the mean of the entire population, but doesn't give information about individuals. All right, so this confidence interval tells you all the people in New York City who do this, if you average them up, they'd be in here. It does not give me what any one person does. One person could be in here One person could be completely out of here, right? Because in a population, the spread is a lot greater than, you pick a sample 61, that's why this thing divides. The spread of the sample is not nearly like the spread of the people, right? And we don't know the distribution here. If we did know it was normal, we might be able to test it out, but we wouldn't use the confidence interval for it, right? They do give us a mean and standard deviation. It looks like this person actually probably wouldn't be that unusual because they're within one standard deviation. But once again, they're not asking about if that person is actually unusual or how to get it. They would just say, is the confidence interval going to get it for you? And the answer is absolutely not. The confidence interval will not tell you about an individual. All right, let's look at the point totals. Part 1, you need to do something about saying or at least performing. So you should say that you're going to do a one sample t interval. If you don't say it, you need to at least show the procedure in some way. So like if you perform the calculation, that is sufficient for like using this formula or the statistics of this thing. That's enough, but it's better to just state it. So one of the points is for stating or doing the one sample t interval. And then they want you, so step 1, I should say, is the conditions check. Sorry, I should start off with that. This is the conditions part. So if you didn't check conditions, you did none of this, right? So for the conditions check, something about this coming up somewhere. And they want you to check randomness in the nearly normal condition. You should check all 4, but they only cared about randomness and nearly normal for this problem. So you do all 3 of those, you get an E. You have to have 1 in order to get the P. You have to have 1, you could have 2 or 3. So somewhere, someone needs to see you're doing the right procedure. If you only checked 1 of these, you get the P. Otherwise, you get the I. So if you did, for example, the wrong procedure, you tried to do a 1 proportion Z interval, well, now you're out of luck. Step 2 is doing the confidence interval. They do say the work is not required in this case because you could just go to the calculator and create the interval. So they allow that so long as you showed and stated what you were going to do. If you show the work, fine. So E is the correct interval. P is you have the correct interval, but your supporting work is wrong in some way. So they allowed certain numbers of mistakes. And an incorrect interval due to a calculation error, like a minor error. So if you had the correct interval but had some kind of wrong support, or you have the incorrect interval due to a minor calculation error. Otherwise, it's an I. So this is actually making the confidence interval. Step 3 is the interpretation of the confidence interval, and they want 4 things from this interpretation. You need to mention something about it being 99% confidence. You need to have something about being an estimate of the population mean. So that why are you creating this? Because it's estimating the average number of the entire population. That's somehow about the population value or true value. And you need to have the context down. So you can't just go, oh, the population means between here. You have to say that it's the number of steps of the employees in New York City who are wearing trackers, all that junk. All right, so it's the context having the number of steps, and all that other jazz in there. All right, so there are 4 criteria here. All 4 get you the E. The P has to have the 99% confidence in it, so you have to say that, and you can have 2 out of 3 of the others. Or let me see, 2 out of 3 of the others. And this says, or you interpret what 99% confidence means. So if you don't say 99% confidence, but you say what it means, that if I took lots and lots of samples, 99% of them would contain the real value. I doubt someone would do that. It's easier to just say it's 99% confident, but they'll take that. All right. So those are the 4 criteria for that. And finally, the last one about can you move it out to the individual. Well, step 4, you have to say no and justify it by saying the confidence intervals can't be used for individual values, something along those lines. The E is both parts. P is you get the first part, but you don't really have a great explanation. It has to be a weak explanation. So realize if you don't say no, you don't even get a point. It's an I otherwise. And when there are 4 parts to a problem, they normally just assign a point to, so like there's, you can get an E. So the way they do when there's 4, basically each E is worth 1, each P is worth a half. If you end up in between, because it's possible to get, 2.5 points, what the grader will do at the AP place, whoever's doing it, they're called AP readers, whoever's reading your exam, doing the grade, what that person will do is they're supposed to use a method that if it's like a strong 2.5, they'll round you up, or if it's a weak 2.5, they'll round you down. So I don't know the super details of all that, but I just know that if it's a 2.5, it could go either way. So normally what I do as a teacher is if you've got a 2.5 or 3.5, I round down just to be safe. So if you have 3.5, I say call it a 3. That way when if we were practicing, we generate an actual score, you got the worst case scenario. But just realize that if you're in between, so like if you got, P, you'd have 3.5 points, and it would really be up to the grader as to the strength of your response, whether they could bump it up to a 4 or whether they would knock it down to a 3. Because basically, if it's 3.5, you're not getting 3.5. You're either getting a 0, 1, 2, 3, or 4. All right? So that's how this one worked. Those are all the answers. This is a pretty good, somewhat intensive inference question. So really tests, do you know what you're doing with confidence intervals? All right? That was AP Problem 4. Be on the lookout for, obviously, AP Problem 5 coming up soon. Until next time.